Okay, we're gonna do a quick discussion or a lecture, kind of overview of Unit 4 on automata, finite automata and pushdown automata here. Let me share my screen here. Okay, let's see how that looks. Okay, again, we'll be looking at finite automata and pushdown automata, and again, also talking about regular expressions a little bit here for this. This gets so far we've done kind of covering topics that are both in programming language course or a computational theory course. Here's our first step really more into theory course. So this sort of stuff is not as applicable through a programming language course, or and you might ask, well, how would you use this in programming? And the short answer is maybe not. We will be returning to this. So for after the fourth unit, we'll spend about 8 units looking at different programming language topics, like memory management or variables or how we call the stack or how loops work in detail, lambda expressions, things like that. And then the last 4 weeks, of course, we'll kind of return to theory here and look at that. And we'll bring up Turing machines, and Turing machines will be based on push-down automata, which we'll be covering here. So this is kind of prep for that before we go back into there. And just to show you that, let's look like this is a Scott's Programming Language Pragmatics textbook. Here and in chapter 2, we did go over scanning, how we create a scanner, recursive descent or table-driven parsing, how we do parsing, and then he has just a little section on the theoretical foundations, what finite automata is, what a pushdown automata is, and stuff. And that is actually not even covered. That's in a supplemental material here. So again, stuff is often not covered in a programming language text, but it's covered big time in a computational theory textbook here. So here's CISPR's Intro to Theory textbook. And again, we start talking about regular languages and context-free languages here. And so right away with regular languages, he introduces them with finite automata. We talk about non-determinism and the equivalence of non-deterministic finite automata and deterministic finite automata. Gets into regular expressions and non-regular languages. And again, talks about context-free languages and push-down automata. And again, we start looking at some of the stuff that we can do with push-down automata, or what we need to do that can only be done with a push-down automata that can't be here. The problem with this, as we'll see, is that a lot of these examples are very theoretical, and they don't really apply to programming languages that much here. Here's another example of that. This is Hofkraft's and Ullman's text. Again, chapter 1 starts with automata. Here, why we study automata, formal proofs, introduction to this stuff, and that sort of stuff. And right away we get into finite automata. What are the ground rules that set up that deterministic finite automata, non-deterministic finite automata here for this stuff. Again, brings in regular expressions and languages here for this, and properties of regular languages here. And again, one of the things we'll get with regular languages is you can define simple regular languages that aren't that you can't define with a normal finite automata. So then, and again, that leads context-free grammars are equivalent to these regular expression languages, and so then you need a push-down automata in order to kind of process this sort of stuff. So again, their coverage of this stuff is, like 260 pages of text. And so we're just going to try to, we're going to delve into this, but not as deeply as some of these textbooks would delve into them here. There's a lot of theory you can get into this. One of the things we will touch briefly, and you'll have option to dive in a little deeply more into, is pumping lemmas. These are kind of little proofs or little problems where you're saying you're trying to push these things to kind of their limits by trying to add more characters or pump these full of certain things. So there's pumping them as for both regular languages and context-free grammars. The other thing is this, the church Turing thesis, and again, that brings us closer to Turing machines here and kind of set some limits of computation with these things. And we'll get into that more, but we'll have an option of that. So, for example, in your prompts here this week, we start talking about finite automata, deterministic and non-deterministic finite automata, and what's the difference between the two here, and how to convert one to the other. We'll briefly go into regular expressions here and talk a little bit about this here, and then we'll talk about working with deterministic finite automata. What we'll do is any automata will convert and to a deterministic finite automata. That's what we'll be working with here, and then we'll talk about push down automata and what that adds to this. This is going to add a stack to our process, and then we'll try to bring this all together and say, well, we've talked about Bacchus-Naur syntax, talk about context-free grammars, regular expressions, these things. How are these all related, and then how do they relate to programming languages and theory for this stuff? But again, and as a bonus challenge, you can do some research into some of these pumping lemmas and this what's called Chomsky normal form, which is kind of a minimal version of a context-free grammar or a pushed-out automata, where we try to find the smallest expression of that language for this. So that's what you'll be doing with your prompts here. Let's talk a little bit about what these are and compare these a little bit. Okay, so let's look a little bit at a finite automata. Now, this is just another name for a finite state machine, which is we have a set of states and we have transitions between those states, and we then, for input into our system, we move from one state to the other here. So like this is an example. So, often we'll see examples of a finite state machine for like an ATM, an automatic teller machine or something like that. This is a similar one. This is a store. You can buy something, pay for an order here, and then if you're paying for something, you go from state A to state B, and once you're in state B, then you can, the store can ship that order, and you go down here, and you can ask for that order to be redeemed, or the different states. I don't find this example all that clear in this textbook. So I'm not going to go over it, but that you can kind of see the idea is that you can move from one state to the other. Now, in computational theory, we generally, in languages, what we often look at is simple inputs and stuff. So we might, and again, you're thinking of a language being like if, and then some expression, or even just the expression would be a number or a letter, and then one of the assignment or one of the operators, one of the arithmetic or Boolean operators, and then some other expression like that. In theory, we tend to even simplify it more than that. So like this is a language for something that it just takes zeros and ones here. And the question is, what kind of inputs or values would this accept? So we have a start area and an implied start state here that goes here. We have our inputs. So every time we get a 0 or 1, we do an input. And then we usually have one or more final states. If we end up in this Q2, we have an accept state, and that's just marked by a double circle in this case. Sometimes I mark it in different ways. But again, if we get an input like this, 1, 1, 1, 0, 0, we'll start here, we get a 1, we go here, we get another 1, we stay here, we get a 0, we go over here, and we get a 1, we go back. And we end up at the state where we have accepted this state for this. There are other ones, so if I scroll down here, let's scroll down and get to this example. Here, this is a state that the final state's here, and we'll only accept strings of zeros and ones where there's at least 1 0 and immediately followed by a 1. So again, we start, if we get a 1, we keep looping in this state, the state here, I guess not the start, this first state here. When we finally get a 0, we go over to the state. So now we've had a 0. If we get more zeros, we just keep in this state. And then if we get a 1, we go over here in this final state. And then if we get a 0, 1, we just stay in this final accept state. So as long as our input has at least one place where a 0 and 1. So if we just have 1, 1, 1, 3 ones, we start and we go 1, 1, 1. We'll end up here and we'll run out of input and we won't be in our accept state here. If we have 1, 1, 0, we go 1, 1, 0, we'd end up here, and then that's end of our string. We would never get over here. So these are the kind of theoretical languages that computational theory deals with, is these languages of. So we might ask, like, can we write a finite state machine that accepts any string where we have the same number of zeros and ones together, or not even together, but throughout the thing, and or a palindrome, like where the first half of the language of a string has to match the second half of the string, or something like that. So we can ask questions like that for this. This is another example of this. This is a automatasimulator.com here. You can build your own little automata here, and you can then give it some languages and see. So I typed in, so this, rather than zeros and 1, it'll accept A's and B's here. So I can start with A, B, and ask, is this going to be accepted or rejected here? So I'm going to start debugging this. It starts at the start state here. It has, this transfer just means, the E means it empty. It just automatically goes here. And then once we're here, I see an A, and so it'll go up here. It's state 0. It's going to see another A, and so that loop here shows that it stays in this state. If it goes a B over here, it can stay. So it stays here. It stays here. Now, this is a non-deterministic one, meaning that a number of the loops also have an empty set. So we could randomly just go over here with the E-like symbol here is an empty input. So without any input, we can go over here, and that introduces some non-determinism, and we could process things over here for this. So it's unclear where we should be, and one of the things we'll look at is for converting from a non-deterministic to a deterministic stuff, we'll have to get rid of all these empty transitions here for this. So again, I'm seeing a number here. And finally, I'll get to my last thing, a B. I'll end up over here, but I won't be in an accept state. I'm trying to figure out here again where they have their accept states. I forget how they mark this as I think this is the marking out. This is the check mark. We want to be in this one at the end, but we ended up here at the end, and so this isn't an accept state. So, one of the problems you'll see is that the AI has trouble drawing these sorts of diagrams, so they'll try to draw it out different ways, but some of the prompts are not the best results. So if anyone finds a good AI for this, when you're trying out different ones for these prompts that can draw out adequate diagrams, I'd be please share it with the class, because I haven't found a great one for that. Okay, so that's just a quick introduction to this stuff. Go through, do your prompts here. That should hopefully explain a fair amount of this to you. The learning activity here, and I'll update. I don't have the assignment here, but I'll put a short assignment here later on this weekend, so you can do it next week. Again, we won't have class this week. I'm out of town this week, so we'll do everything online asynchronously this week. I will be available, particularly evenings, for help, so feel free to email or text me. And I can answer questions and stuff like that. Okay, let's stop this.